Welcome to a video series about the scientific basis for the application of microcurrent. Since it covers a wide range of topics, we have divided it into several chapters. The first chapter is about the history and basics of microcurrent application. The second chapter focuses on the effects of microcurrent on cells and tissue. The third chapter discusses the effects of microcurrent on pain, blood flow, muscles, and various electrochemical effects. Let's start with the first chapter and the first main topic, the history and basics of microcurrent. Microcurrent is a fascinating aspect of biological science. This unique application harnesses the subtle power of electricity to interact with biological systems using specific frequencies. In this video, we are going to delve into the history and basics of microcurrent application. An introduction to microcurrent, the fundamental physical principles. Microcurrent involves the application of extremely low levels of electrical current, mirroring the body's own natural internal currents, which are integral to cellular and body functions. What is microcurrent? Electricity flows through the bodies of all mammals, controlling and regulating many of their basic vital functions. Microcurrent mimics these natural currents and supports various physiological processes without causing any sensation or discomfort because the applied currents are extremely low in strength, in the range of 50 to 1000 microamperes or millions of an ampere. It is nearly imperceptible but can be very impactful and is, among others, utilized to support cellular activity and optimize tissue functions. Application in humans. Microcurrent involves the application of a very low-level electrical current to the body. Electrical current, often simply referred to as current, is the flow of electric charge through a conductor. Conductors are substances that allow the flow of electric charge, typically in the form of electrons or ions, with minimal impedance. Metals and electrolytes, for example, are conductors. An electrolyte conducts electricity by means of the movement of ions. These moving ions carry electric charges and are essential for a range of physiological processes in living organisms, particularly nerve and muscle functions. However, the effectiveness of microcurrent depends on its exact mode of application. The variables include the pulse frequency, the signal shape, and the electrode placement. Developers of microcurrent applications must possess a high level of knowledge, skills, and experience in order to combine these parameters in such a way that the maximum possible effectiveness is achieved for the desired area of application. Types of current. There are two main types of current, depending on fundamental differences in the direction of charge flow. Direct current, or DC, is a fundamental form of electric current characterized by the consistent and unidirectional flow of electric charges. Alternating current, or AC, on the other hand, is an innovation attributed to the pioneering work of Nikola Tesla. AC introduces a dynamic dimension to electric currents through its periodic reversal of charge flow direction. This oscillatory behavior gives AC its characteristic frequency, which is measured in hertz. Currents of various frequencies in the human body include brain waves, 0.5 to 150 hertz, heartbeat, 0.05 to 100 hertz, muscle activity, 20 to 500 hertz, and nerve signals, 1 to 1000 hertz. We can produce and hear sound waves in the range of 20 Hz to 20,000 Hz, and our body naturally emits extremely low frequency, or ELF, electromagnetic fields associated with physiological processes. These frequencies are usually in the range of a few Hertz to a few kilohertz. Microcurrent applications can be categorized according to their frequency spectrum. 0 Hz, galvanic current, 1 to 1000 Hz, low frequency, 1000 to 100,000 Hz, middle frequency, over 100,000 Hz, high frequency. The following forms of application apply electrical current to the human body. Microcurrent electrical therapy, MET, microcurrent electrical nerve stimulation, MENS. MENS focuses on stimulating nerve activity through microcurrents. Cranial electrotherapy stimulation, CES. CES employs microcurrents to the head. Electrical stimulation, ES, neuroelectric therapy, NET, transcutaneous cranial electrostimulation, TCES, transcutaneous electrical nerve stimulation, TENS, microelectromedical stimulation, MEMS. The electric circuit and its equivalent in cells, organs, and the body. An electric circuit is a network of interconnected conductors and components that forms a pathway for the movement of electric charge. In the realm of biology, the concept of electric circuits helps us understand the behavior of biological systems, from individual cells to entire organs. These systems exhibit ionic conductivities and electric potential differences, which can be compared to electronic circuits. Such analogies help researchers comprehend the intricacies of biological signaling and function, opening doors to advancements in the medical and physiological sciences. The electrical connectivity of different tissues of the human organism depends on the respective fluid content. The more ions there are in a tissue, the higher the conductivity. Good conductors are blood, urine, lymph, cerebrospinal fluid, parenchymal organs, and muscles. Relatively poor conductors are adipose tissue, tendons, joint capsules, myelinated nerves, and bones. Insulators are the stratum corneum of dry skin, nails, and hair. Historical background and discovery. The discovery of the effect of electricity in the body of vertebrates dates back a long time, to the 18th century, with Luigi Galvani's experiments discovering that muscle movement is caused by electrical forces, evolving through the centuries from basic bioelectric studies to the sophisticated applications in today's microcurrent technology. Luigi Galvani, 1737 to 1798, Italian physician and physiologist. Alessandro Volta, 1745 to 1827, invented the first chemical battery. Robert Bartholow, 1874, American physician who conducted one of the first documented cases of electrical stimulation of the human brain. Albert Abrams, 1863 to 1924, developed devices like the oscilloclast, which purportedly used electrical currents to treat various ailments. George Lakhovsky, 1869 to 1942, proposed that living cells emit and receive electromagnetic radiation and used this concept to develop therapeutic devices, furthering interest in electrical stimulation for health benefits. Dr. Thomas W. Wing, chiropractor and acupuncturist Dr. Wing in the 1970s developed the first microcurrent devices designed for therapeutic use. Modern research and clinical studies. Throughout the late 20th century, numerous studies and clinical trials were conducted to investigate the efficacy of microcurrent application. These studies provided evidence supporting its use in various medical and aesthetic applications, such as wound healing, pain management, and facial rejuvenation. Microcurrents and their biophysical effects on biological systems. Microcurrent application can enhance and regulate the cell metabolism through a number of mechanisms, such as increasing cellular energy production, influencing ion transport and cellular signal transmission, optimizing cell membrane potential, stimulating protein synthesis, improving blood circulation. These combined effects can contribute to improved cellular function, enhanced regeneration, and other positive effects.